EDX Decision 1, Graphs and Networks 1, Definitions and Spanning Trees. Modelling with graphs. In the history of graph theory, there is a classic example called the Seven Bridges of Königsberg problem, which was resolved by Leonhard Euler in 1736. And the problem here is there's a town called Königsberg and you want to travel across every bridge once and get back to your starting point. So for example, if I started here, started to cross every bridge once, is it possible to get back to my starting point? And you soon reach a point where you are stuck. There's nowhere I can travel from there. And this was a classic problem, and Euler resolved it by turning each piece of land into a node. So there's north of the river, there's the island, south of the river, and the landmass to the right is another node. And then he put all the bridges on. So there's two bridges from the north of the river to the island, two bridges from the island to the south of the river. There's a bridge to the right, there's a bridge from the north, and there's another bridge from the south. And when you look at the order of the node, you get 3, 5, 3, 3. And because there are 4 odd nodes, it's impossible to traverse. This is non-traversable because there are more than 2 odd nodes. In this graph, a town has been associated with each node. The edges represent, for example, direct bus routes. So we've got towns called Cheddar, Glastonbury, Yeovil, Street and Wells, and the edges represent direct bus routes where available. Notice this is not a map, and the edges represent a relationship between the towns. If we add a value or a weight to each of the edges, this makes it into a weighted graph or a network. So we're now looking at a weighted graph, or you can call it a network, where the weighted edges represent the distances for the direct bus routes between the available towns. And we could represent this as a matrix. So you could turn it into a matrix. So we could have Cheddar, Gloucester, Yeovil, Street and Wells, Cheddar, Gloucester, Yeovil, Street and Wells. So there's no link from Cheddar to Cheddar or Gloucester to Gloucester. There's no direct link from a town to itself. From Cheddar to Glastonbury is 35, so Cheddar to Glastonbury, put that in twice. From Cheddar to Yeovil, there is no direct link, and you can show that by either a dash or you can put it in as infinity. There is no finite answer. From Cheddar to Street, there's no direct link. From Cheddar to Wells is 24. So from Cheddar to Wells is 24, and these would be infinity. From Glastonbury to Yeovil, there's 42 direct, so that would be 42 as well. From Glastonbury to Street is 6, so that would be 6. And to Wells is 24. 24. To Yeovil to Street is 30, so Street to Yeovil is 30. And from Yeovil to Wells, there's no direct link, so that would be infinity. Yeovil to Wells, infinity. Street to Wells is 35, and that means it must have a 35 there. So you can turn it into a matrix, the same information. What questions could we ask about this network? In this course, we'll be looking at some specific questions we could ask. We'll be looking at minimum spanning trees, so that might be looking at the shortest way to connect these towns together on a single network. We could be looking at the shortest distance between various towns, and we could be trying to traverse every single edge once and turn it into a route inspection problem. Solving network algorithms is an important part of computing and modern technology, and we'll be introducing you to some of the techniques used in some quite advanced mathematical applications. In the next session, we'll be looking at minimum spanning trees using Prim's algorithm.